Hello, all. Happy Friday, May 1st. Say goodbye to April and quarantine. Hopefully, May is going to be looking a little bit more in our favor, that we can actually get out and do a little socializing, as long as you keep your distance. All right, so today is a topic called mathematical induction. What I view this is as a formal mathematical proof that a rule is always going to work. This is actually the last topic for the sequences and series unit. So once you have all those checkpoints in, I can assign a grade to the math unit or performance task. And we only have a few more days of limits left. I don't actually have that unit yet from Mr. Abundus. But once we get through with that one, we are done with the semester. So 15 days left. All right, so what we're going to do is we're going to look at the partial sums for a series of odd numbers. So if I had my sequence or my series of odd numbers and I added them up, the first sum I would get is S sub 1 was equal to 1, S sub 2 is equal to 4, S sub 3 is equal to 9. Hopefully you're seeing the pattern. S sub 4 is equal to 16, then we have 25, and if we added this last set, we had 36. So my rule would be the sum of a certain set of numbers for this odd number series would be n squared. So this is 1 squared, 2 squared, 3 squared, and so on for my first term, my first two terms, and my first three terms. All right, so what we're going to do here in a little bit is we're actually going to prove that that's an always true statement for any natural number n. Okay, so mathematical induction is proving that something's true in its most basic case. You're going to prove that if in any case is true, then the next one must be true as well. So in other words, if I go back to this example, this would be my sixth term or my sixth term series. So what I'm going to do is I'm going to prove that this is going to work for 7 terms in the series as well, or one more term than the previous term. Okay, so this is kind of called domino effect. All right, so here is how you prove how you do proofs using mathematical induction. What I would do here is I would pause this and just kind of read through it yourself. And then we will actually go through all the steps in the problems that are coming up in the next example. All right, so those of you that don't like to show your work or show detail probably aren't going to like this very well, because it's really very specific on the steps that you have to show. All right, so I'm going to prove by mathematical induction, which is a specific process, that 1 plus 3 plus 5 plus 7 plus the next term would be 2n minus 1 is equal to all natural numbers n. So basically what we're doing is we're proving that very first warm-up slide that we did. All right, so step 1, if you looked at your steps, is the first thing you have to do is plug in n equals 1. So if I use this piece of the puzzle right here, I have 2 times 1 minus 1 is equal to 1 squared. And that is a true statement. So now what I have to do is I have to assume that it's true for n equal to any number k. So step 2, I have to assume that it's true for n equal to k. So what I basically do is I just take my statement that was given to me up here at the top, and I change my n to k. So I have 1 plus 3 plus 5 plus 7 plus, and this is going to change to 2k minus 1 equals k squared. All right, so step 3 is where we have to prove that it's also true for the next number in the sequence. So we're going to prove truth for n equal to k plus 1. So in my statement up here, k is equal to 1. Now I'm going to prove that it's true for n equal to k plus 1, or n equal to 2. All right, so I have this statement right here, which we're going to use here in a second. So when you do that step 2, always note that equivalent statement that you have there. Okay, so now I'm going to say 1 plus 3 plus 5 plus 7 plus the statement that was originally given to me, 2k minus 1. Now what I'm going to do is I'm going to go ahead and substitute this k plus 1 in place of my n. So now I have plus 2, k is going to be equal to k plus 1. Tried to change colors and it didn't work. Minus 1. And on the other side, my k is going to become k plus 1 squared. I changed my colors for you here. It's not working today. Okay, so right here is where I changed my original n to k plus 1. This is my original statement right here. Okay, so now comes the algebra. So now what I'm going to do is I'm going to just basically work the algebra out, and I should end up with the left side equal to the right side. Okay, so this statement right here, I can substitute that 2k minus 1 is equal to k squared. And then here I have, if I distribute my 2, I have 2k plus 2 minus 1 is equal to k plus 1 squared. Okay, so mathematically, I should be able to work this out. K squared plus 2k plus 1. If I FOIL out k plus 1 quantity squared, I get k squared plus 2k plus 1. The left side is equal to the right side. So I'm done. So the last step is where you make the final statement by the principle of mathematical induction. We can say that 1 plus 3 plus 5 plus the original statement 2n minus 1 equals n squared is true for all natural numbers n. Okay, so I believe that this is an abbreviation of that statement that I just wrote above. Not quite sure what that is standing for. This is a first for me. All right, so that took a little bit of time, so these notes might get a little lengthy today. I'll start shortening some things up and abbreviating some wordage for you. Okay, so remember, this is basically just a formal proof. All right, so now I'm going to prove this statement, 4 plus 8 plus 12 plus 16 plus 4n. So if you notice, all of the terms in the sequence are multiples of 4 is equal to 2n times n plus 1 for all natural numbers n. So step 1 is where you simply start your statement off by saying n is equal to 1. So I have 4 times 1 equals 2 times 1 plus 1 plus 1. So I get 4 equals 2 times 2, which is equal to 4, which is a true statement. So step 2 is basically where you recreate the statement and just make n equal to k. Okay, so we're going to assume truth for n equal to k. And basically you just recopy the first statement. And change your n to k. Okay, so step 3 comes the proof. So now we're going to prove truth for n equal to k plus 1. So from my original statement, I have 4 terms. If I added those up, I should get a multiple of 4, basically. So now I'm just going to what happens if I have 5 terms in my sequence. So I'm trying to prove that if I add a term, basically it's still a multiple of 4. All right, so I have 4 plus 8 plus 12 plus 4k equals, oh, I forgot to add my plus 1, sorry. So plus 4k, that's my original, plus okay, so now I'm going to take my 4k and I'm going to change my k to 4k plus 1. Can't get my colors to work very good today, sorry about that. And that should equal this statement, but my k's changed to k plus 1. So I have 2 times k plus 1 times k plus 1 plus 1. Okay, so if I look here, this blue one to work. So here is my original statement right here. Oh, there it's working. Okay, so right here, those two blue statements match, so I can use substitution. And I can substitute my original statement in for my 4 plus 8 plus 12 plus 4k. So I have 2k times k plus 1. And then I still have my 4k plus 1. That should equal, let's see if I can simplify this a little bit. That'd be 2k plus 2 times k plus 2. Now it's just a matter of simplifying. Okay, so there is my 4k plus 1. There's where I distributed. And there's set k plus 1 is k plus 2. Okay, so if I distribute my 2k, I get 2k squared plus 2k plus 4k plus 4. I'm trying to get my left side equal to the right side. So if I FOIL this out, 2k times k is 2k squared. My outside and my inside is going to be 4k plus 2k, which is 6k plus 4. This is the fun part, because it's just algebra. So I get 2k squared. I can put these two together and get plus 6k plus 4 equals 2k squared plus 6k plus 4. So since I ended up with the left side equal to the right side, I can now make the statement that by the principle of mathematical induction, so we're going to call it PMI, shorten that a little bit. I can say that 4 plus 8 plus 12 plus my original statement 4n is equal to 2n times n plus 1 for all natural numbers. All right, so what you're doing is you're proving the statement by a mathematical method other than just continuing to add numbers to the sequence and proving it that way. So basically a formal proof, which you did a little bit of that in geometry, but probably not too much. All right, so one last one here. This one shouldn't be that bad. Okay, so we're going to prove this, that 5 to the power of n minus 1 is divisible by 4 for all natural numbers n. All right, so step 1. Easy part, n equals 1. 5 times 1 minus 1 equals 4. And we know that 4 is divisible by 4. So our starting point is just with the very first term. All right, so step 2. This one's going to be a little bit different. So we're going to assume that 5k minus 1, this is where we substitute n equal to k, is divisible by 4. Okay, so then we're going to have to create a new statement here. We're going to have to assume that 5k minus 1 is divisible by 4, which means whatever the number is a multiple of 4 for all p-values. So when you're doing these divisibilities or multiples of, you have to make this new statement where you're taking a number and multiplying it by, in this case, the 4. So what I should get is a number that's going to be divisible by 4 by showing if I multiply it by 4, it's divisible by 4, if that makes any sense at all. Okay, so step 3. is we're going to prove that this is true for k plus 1. Okay, so if I take my original statement, which is 5k minus 1, or 5, all right, so, okay, so we take our statement and we simply take our k and substitute k plus 1. So I have 5 to the k plus 1 minus 1, and I want to show that that is going to be equal to 4 times some number p. Okay, so we're going to have to use a little mathematical knowledge in order to work on this left side. So if you think about your rules of exponents, you add your exponents when you're multiplying two values that have the same base. So I'm going to take this 5 times k plus 1, and I'm going to change it to 5 times 5 to the power of k times 5 to the power of 1 minus 1. Equals 4 times some number p. Okay, so I need to take my statement on the left and somehow figure out how I can get a 4 out of using the numbers 5. So I'm going to take my 5 and change it to 4 plus 1 to the power of k. Sorry, I used the wrong number there. So I need to use my 5, just my constant 5, and change that to 4 plus 1. Sorry about that. And I still have times my 5k minus 1. And I want to still show that's equal to 4 times some number p. So now if I distribute my 4 plus 1, I get 4 times 5k plus 1 times 5k minus 1. That's going to be equal to, hopefully, 4 times some number p. Okay, so now if I look back at my original statement right here, I know 5k minus 1 is equal to 4p. So I can substitute 4p right here. And I have my 5k times 4. So all I did was a substitution. I want that to be equal to 4p. So now I can factor out a common factor 4. So I have 4 times 5k plus p equals 4p. And keep in mind that this was some number p, any number that we want to choose. So now over here, my 5k plus p is representing my 4p. So we can let p equal 5k plus p. So now I have 4p is equal to 4. Okay, so right in here is where the math gets a little bit sticky. These aren't going to get overly complicated for you. You should just be able to follow the notes and eventually get the sequence to the problems pretty easily. Okay, so now I can make the final statement by principles of mathematical induction. 5 to the n minus 1 is divisible by 4 for all values, for all natural numbers. All right, so again, that was the final lesson. It was a little bit long today. Sorry about that. I am going to go ahead and put the worksheet in OneNote for you. I think there's 4 of them you have to do, but I will give you Monday to work on that. So you'll have Monday to complete. Hopefully I can put some grades in for performance tests on Tuesday. We'll probably start limits on Tuesday, and then I'm sure you all got the email that from now on Wednesdays will be no assignments. So please, please, please use this extra time to get caught up if you're behind. Summer school is definitely a possibility if you're behind on May 22nd. Basically, there's no math analysis class now offered in the fall, so to go on to the next class, you kind of have to pass math analysis. So use the weekend too. I know it's no fun, but if you're behind, that's what you need to do. Have a great weekend.